Hello and welcome. Welcome to this video. In previous video, I have given a step-by-step process how you set up the PLC hardware, give the address to the modules, and it's like setting up the problem statement and how you're going to solve the problem. So we have a problem like three machines are there. Let's repeat it again. There are three machines, each with its own start and stop buttons. Each start button is to have a steering circuit, right? The PLC logic, ladder logic to operate all three machines. Now, in this video, we are going to find out all these four. We are going to execute all four requirements of hardware and software. Partly we have done in the previous video, and then design software solutions, like in the software what are the things we need, and then we will write the ladder logic for PLC, and also we will execute the testing of the logic. Now I'm not going to the details what requirement is necessary for learning this. Anyone can follow up this video with the basic knowledge of computers and controllers. Yes, obviously, if you are watching this video, you know the basic principle how a computer works. And then, okay, so we will go through the problem solving sections. We need PLC hardware, obviously, to do the testing and programming. To learn the PLC thing, it's better that you do with real PLC. Now, in case you do not have real PLC hardware and software, you can do one thing. Trial version you can download from internet and then install it, and the trial version can work for 2 weeks, 14 days, and then you can practice for 2 weeks. It comes with the simulator as well, so simulator should also work for 2 weeks. And then previous software design documents. In this part we will go through, so we'll actually break down the problem into sections, like here. A machine to be operating as per ceiling method, that is, after per cycle, operator has to press the start button to restart the machine, and each machine has two DI, one DO, that is start button, stop button, and an output for motor or machine. So I have a list here that is for all three machines. So machine 1 we have 3 tags, 2 input 1 output. Machine 2 we have 2 input 1 output, and machine 3 we have 2 input and 1 output. Sorry. Now the stop button that is connected to PLC is NC type, and start button that is connected to NO type DI. So NO type means the switch is normally open type. NC type means the switch, the stop button switch, which has a contact that is normally connected. That means it's like you have a switch, and behind the switch there is a contact connected through the spring that connects and disconnects as per the switch operation. For NO type switch, that contact is normally open. So when the push button is pressed, when the push button is pressed, it gets connected like this. Now, if you follow my fingers here, it's like normally open switch, and if operator press, it connects to the other contact. So actually current flows through the contact when it is connected, and the other side of the wire contact goes to the PLC DI module, and the DI module sends that signal. Similarly, the stop button is normally connected type, like it is connected, like this one. So someone presses this side, it goes down this way. So it breaks the circuit. So this is normally connected, and see when contact is connected. If someone press, it becomes like this. So it's normally connected, but when someone activates it or press it, it becomes disconnected. So the current circuit, flowing circuit breaks, and then which previously normally the signal was going to the DI input. Now it's not going anymore. So PLC gets a negative signal like 0. Okay, so the second two input is, I hope you understood well, machine motor. The machine will be something that will operate, either it can be motor, or it can be either valve or something like that. But we assume that machine has a motor. Okay, sorry. So while doing this software design thing, we come across something like this assumption. We have given a tag name that is machine dash mod dash 1, but we don't know whether that machine has a motor or not. So that's why we have another tab, assumptions. So when we discuss this document with client or our customer, actually we go through the assumption as well. So when going through assumption, client or customer correct if they find something obvious mistake or obviously wrong assumption. So here we assume that machine has main active device as motor. Okay, so that's how we name it, machine motor, which shall be turned on off by PLC digital output. So this is our assumption. Now we're quite clear with the process, with the design of this documentation part. We're going to write the ladder logic. So let's open our TI portal. We have created some blocks. In previous video, I have shown you that why we need to create this block, all underscore di, all underscore do, all underscore ao, and then all underscore ai. So this is to actually save, I would say, all the digital input and analog input or reading from the module are saved in a data block, one for DI, one for AI, and then that saved data shall be used inside the ladder logic or inside the PLC program. And then whatever the decision or output shall be saved in a data block, that is digital output and analog output, which then at the end of the PLC program or end of the scan cycle, you can say, we can transfer those data, digital output and analog output, into the module, PLC module, output module and analog output module. So this is how we have designed this software. We are going to design that way. Okay, some of the terminologies when I'm saying you might not be familiar at this moment, but bear with me. We will come to those terms as well, like scan cycle, end of the scan, or something like that, end of the program. So all those terms we will come to later. We will have the discussion about that also. So this is how we have designed. We have few networks. I will go step by step. So this is the main program sweep cycle. We can call it a OB1 or main program. In Siemens PLC, each PLC, irrespective of which series it is, S7, 200, 1200, 300, 400 or 1500 series, each one has a main program block or OB1. That is the cyclic block. It executes continuously. So it starts from the beginning. Beginning means the network 1 and ends with the scanning of the last network. Whether the last network maybe it may be now in this program we have only 5 network. So it will execute 5 network and then go to the next network 6 and there is nothing. So after this it will rescan again this block from the network 1, 2, 3, 4, 5, 6 and then it goes back to 1, 2. So continuously that way it will keep scanning. Keep scanning means reading the program and make the decisions, send the command output. We'll go through that. So let's do that manually one by one. In the network 1, what we did, we have a always true bit. So what is this? When you turn on the PLC and PLC goes into run mode, this bit goes on. So by default, always this bit will be, and then we have all the inputs, all the digital input for the machine, all 3 machines. We are moving the status of the digital input from the module to the data block, the all DI. You see, the all DI. We are just saving the status from the module into the data block. That's what we are doing in this network. Sorry. And the network 2, the machine 1 ladder logic is done. In this network, I'll give you a clue what is the ceiling circuit. This is a ceiling circuit, it is called. Someone also calls this as a latching circuit, but latching is not proper word here because some manufacturers, some PLC vendors use latching for set and reset. So we will be using it as a ceiling circuit, still-in circuit. So now the start button for the machine 1, it has a no instruction, and then stop button, it has a no instruction. And then we have the coil for the motor machine. Sorry. And then the same machine bit is used parallel to the stop button, and that's how it creates a ceiling circuit. Okay, so when is now remember the stop button is NC normally connected. It's like someone already has pressed the button if it was NO button. It is opposite of NO button, that's normally connected means it's already on. When no one is pressed this button is already on. So its status of this input is 1 by default. By default means when the panel or PLC module has power and switch, your control circuit has power, then it is by default whatever the status, then it is a by default status. So by default this stop button has a status 1 and start button which is normally open means current cannot reach to the digital input module. So it's the open circuit. So when operator press the button, start button, that circuit, NO circuit, closes the contact, and the current reaches to the digital input module, and it reads as 1. So then this is 1, this is 1. If two NO used one after another, that is called AND logic. So this and this, 1 and 1 is 1. So the status moved to the digital output. Here we have a bit, a data block bit, that is all DO bit. Now we have a status 1 1, and this is also 1. And remember one thing, while reading the ladder logic, remember this is like positive 24-volt supply. On your right side, the end terminal is grounded, and this is like load LED. Okay, so same thing. This is one machine. The same thing is for machine 2. No difference at all, except the bit address. We will come to this later. So now for the machine 2, if operator press this one, and this is because this is already NC, so it has a status 1. So 1 and 1 equals to 1. Go to machine 3, and machine 3 also has same logic. Operator press this start button, stop has already status 1, so 1 and 1 equals to output 1. So the machine starts. Now when the machine starts, what will happen? This is a data block, right? So we have always 2 bit which turns on immediately after the PLC powered on and goes to run mode. So we have a audio machine motor output from this data block bit. This output from the data block bit assigned into the real module digital output channel, like the channel Q0.0, 0.1 is equal to 3 machine, 3 digital output. So the status from the data block assigned to the real module output is actually connected to the machine contactor. We will tell you what is contactor later on. So that's how the motor turns on. After scanning this fifth network, the motor or machine actually turns on. And during this, before this, there was only logic that was being executed. So now, when after finishing the first scan, it goes back to here and goes back to here in network 1, and then it reads again all the input, and then it reads the network 2, and then it's network 3 and network 4. But in this time we have a output that is already on. So now we will have 2 parallel bit that is on. We have some problem in this logic. Something is done wrongly. There is error, and there is homework for you to do. What is the error? Let's scan network 2. So we have operator has pressed the start button, and stop button is already connected, and then motor is or machine is already running. So this is also on. So now we have all the bits turned on. What will happen next? So I go to network 3, all the bits are turned on. Go to network 4, machine 3, all the bits are turned on. two digital input turned on, digital output turned on, and digital output bit that is also turned on. So what is the next you can guess? Pause the video, think, and comment below. Okay, so let's correct the mistake. Now, what will happen if operator release the start button? Because the start button is normally open, the contact also will be opened, and for that reason, the status will turn to 0, and 0, 1, and this will become 0. So, machine also will be stopped, and when the machine stops, you have to restart again. So this circuit is not at all a what is called ceiling circuit. Ceiling circuit will be something like this. Your stop button should be here, either this side or this side. It doesn't matter. It should be in series. We delete this. This here will be start button. Sorry. Now this is the correct ceiling circuit. So we have start button. Operator starts by pressing the push button. Once the output has started, in the next scan, second scan, if operator has released the button, start button, it will keep on the output because of this parallel instruction. This instruction has a bit that is already turned on in the first scan when the operator has pressed the bit, and this is we are executing in the second scan. So operator when release the what is called switch or push button, so the this output will be on through this parallel network. Now in case the power fails, the stop button, which has a NC circuit will, because there is no power, so digital output will go off, and output also will go off. And for that reason, and this will be a ceiling circuit, because next time this is off, and this will also be off, and then it to turn on, operator has to press again. That's what it is. I hope you're clear now. Yes. So similarly for machine 2, we have a little thing to correct, as this one is here and this goes here. Start the button, stop is already connected, so 1 1 equal to 1, and when operator release this, because this output is this one, this bit is already previously turned on by turning on the push button, so it will be kept on through this side. This will be on, this is on, and this will remain on unless and until someone press the stop button or power goes off. Similarly for machine 3, we have some little correction here. Okay, so this is the correct ceiling circuit. We have start button, stop button, which is NC. So by pressing the start button, we can start the machine, and the machine bit will remain turned on to this circuit, and this circuit will latch up the machine 3 output. Okay, so unless and until the stop button pressed, this will remain on position, and that's how all three machines now have a ceiling circuit. The output always goes from the data block status bits to the module digital output module bits. So hope now the program is clear. We can save it and then we can execute the simulation. With simulation, I think we're running. Yes. Okay, we're running the simulation. Let's download and download it. Now what we can do, we can create a watch table by which we can actually turn on and off the switch. I 0.0, I 0.1. This is Q for machine 1, Q 0.0, machine 1 motor. This is for monitoring. You have to press this goal sign to go online. So now our PLC watch table is connected with the real PLC, but there is no real PLC right now. I have a simulator running in my laptop. So the simulator is in run mode. If I stop, you see the execution system clock bytes also stop. Start. Sorry. Okay. So now remember, stop button is connected by a NC, normally connected switch. So normally connected NC switch is something like is already on by default, as I told you earlier. So if at this moment, if we press the start button, pressing is something like this, Control F2, see the machine is running. So we have pressed the switch. Pressing the switch is something like, let's go online with this block, machine 1. So we have pressed the start button. Stop is already NC connected, so 1 1 output is 1. Now all are on. So in this few seconds, maybe 1,000 times already this ladder logic scanned. So we cannot actually go one scan and the next scan. That push button can goes up, return to its default position in any scan, anytime. So anytime it goes back, like it goes to 0. Okay, okay, we can do it from here. Let's turn off. So we turn off the start button to simulate that push button has returned to its original position. But remember, as I told you, this ladder logic will keep the output on because of this parallel bit. The same output bit is used parallel to the push button, which is the start push button, which has now returned to its off position. And now the machine will keep running unless and until the stop button is pressed. or power goes off. Power goes off, we can simulate that by stop. So stop, run. You see, it's like machine has stopped. So to run the machine again, you have to go back again to the initial default position. So we have default position like this. Uh, go to, this is NC, stop normally connected. So go back to this. It's like this. This is already green, already on. So now we start by pressing the start button. We have to check why it's not working from there. Okay, let's start from here. It's starting. Machine is starting. Yes, machine is now running. Now release the start button. It's like turning off the start button. So okay, any reason for nothing there. Release the start button, but machine is running. So now you can see how we can it, implement the ceiling circuit. So this is a ceiling circuit. Now we are going to simulate the stop button. If we want to stop the machine, we can press the stop button, which is by default on. If we press it, the circuit will break and the machine should stop. Now press, you see the machine has stopped. Go back to ladder. Yes, machine. Similarly, the same logic we have repeated two more times for machine 2 and machine 3. Now you know how you can simulate using the watch table as well, and you can use the simulator to simulate the on and off, run and stop of the PLC function. Thank you so far for this video. It is, I think, a quite long video. So we will do one more video for the example one to cover some of the design and panel side, hardware side of this example.